All right, so we're ready to finish out section 5.1. So this is the second video, part B of the video. The last one we went about an hour, and I didn't want to go too long of a video. So objective 3, we're going to determine coterminal angles. So first, let's define what coterminal angles are. So two angles in standard position with the same initial side and the same terminal side are called coterminal angles. Oops. Right. So some examples of coterminal angles would be the following. Right, so if we have, say this situation, so we got XY plane, and then say we have this as my initial side, and then let's say this is 30-degree angle. Right, there's my terminal side. So then another angle that would be coterminal is essentially if you add like another revolution, right? So let me come in with a different color. So if we were to go around one full time and still land right over top here, right? So in other words, 30 degrees plus 360 degrees, right? Which is 390 degrees. Would be coterminal, right? So what we did is we took 30 degrees, oops, and we added 1 times 360 degrees to it to get 390 degrees, right? So another example of this is if we start out with my 30-degree angle again. And then let's say I add like 2 rotations to it, right? So I'm going to go around one time and then one more time and still land onto the same terminal side, right? So in other words, I took 30 degrees and I added 2 times 360 degrees to it. That would be equal to 750 degrees, right? 720 plus 30, right? So those would be coterminal, right? So then we'll start with the 30-degree setup again, one more time. So let's say that's 30 degrees. Then this time, let's say I'm going to go a rotation, but go one rotation in the negative direction, right? So in other words, I'm going, whoops, no, that's right, yep, over to here, right? So in other words, I went negative 360 degrees. Whoops. Right. So that would be 30 degrees plus negative 1 times 360 degrees, right? So that puts me at negative 330 degrees, right? So 30 degrees and negative 330 degrees would be coterminal, right? So two angles in standard position are coterminal if their measures differ by a multiple of 360 degrees or 2 pi radians, right? In other words, a way we can write this symbolically is if I could say, we could say like alpha and sigma are coterminal, angles if and only if alpha equals theta plus n times 360 degrees, or alpha equals theta plus n times 2 pi, where n is an integer. Right? Another way we could write that mathematically is I could say n epsilon and then the boldface z, the symbol for integers. Right? So if you're not familiar with this notation, it's something you could start to get familiar with. We use a lot of different notation in advanced mathematics, so maybe if you're a STEM major, that might be important for you. So so this symbol, as I said, this is epsilon, and it basically means within. Right? This boldface z symbol, that is the set of integers. Right? So you might be weird why use a z for integers, and it comes from a German word zeta, which stands for integers. Right? So the set of integers looks like this. Right? So we have the whole numbers, and then we're adding on the additive inverses, right? The negatives of each of the numbers, right? So we have positive and negative numbers going from both directions, but there's no fractional or decimal part, right? These are all, well, this is what we call integers, right? And these three dots here, right? It's called an ellipse, and that's meaning that's going in both directions forever, right? Something else that you might see in advanced mathematics is this statement if and only if. So logically that means it can go both directions, right? So if alpha and theta are coterminal, we know the part after the if is true, right? Also, if the part after the if is true, that means that theta and alpha are also coterminal, so we can go both directions, right? An if and only if is often shorthanded with basically an if with two f's. Right, so this is the same thing as if and only if. Right? All right, so now we have some examples working with coterminal angles. So we're asked to find an angle that's coterminal to a given theta, but we want it to be in between 0 degrees and 360 degrees. Right? So essentially, like in part A, we start with theta, which equals 1,230 degrees. We essentially want to keep subtracting off 360 degrees, right? Because we're bigger than 360. Keep subtracting 360 so we keep getting coterminal angles. And we want to stop once we get a value in between 0 and 360. Right? We're trying to remove all those unnecessary rotations, right? So looking up here, 30 degrees is the same as 750 degrees in a lot of, trig applications, right? So we're starting and stopping at the same point. So what we can do is remove all those rotations because they're unnecessary, right? So we could take 1,230 degrees, subtract off 360 degrees, and you get 870 degrees, right? And then we could take 870 degrees, subtract off 360 degrees, and we get 510 degrees, right? Then we could take 510 degrees, subtract off 360 degrees, and we get 150. Right, so finally we're where we want, right? So this is the angle that's coterminal that meets this criteria, right? So basically what we did is we took 1,230 degrees, subtracted off 363 times, right? So that would be 3 times 360. which would equal 150 degrees, right? So that's maybe the quicker way to get it, but sometimes it's not so easy to know how many of the 360 degrees we can take off, right? So then part B, you'll notice that theta is a negative value, negative 315 degrees. So since we want to get in between 0 and 360, in this case we want to add 360 degrees to it, right? So if I take negative 315 degrees and add 360 degrees to it, then that lands me at 45 degrees, right? And that meets our criteria, right, of being in between 0 and 360, right? So then example 6 is very similar, except we're dealing with radians, right? So we want to find a coterminal angle to theta that's on the interval from 0 to 2 pi, right? And in case you forget this interval notation, right, you should already know that, but just in case, remember the bracket indicates that we include that value, and the parenthesis means we do not include that value, right? So another way to show this is basically, let's say alpha is the coterminal angle. We want to find an alpha that's in this interval, right? So alpha can be equal to 0, but it cannot be equal to 2 pi, right? Because that's what that parenthesis indicates. So not included, and the bracket means it's included, right? And that's called interval notation. Right, so for part A, we have theta equals negative pi over 8, right? So remember, we're not adding 360 degrees since we're in radians. We're going to add 2 pi to it, right? So since we have a negative value, you don't want to take a similar, idea here, as we would have negative pi over 8. I'd want to add 2 pi until I get something in between 0 and 2 pi, right? So if I add 2 pi to this, this would be negative pi over 8. I want to get common fractions, so we could get a common denominator of, I want to get common denominators, right? So we could get a common denominator of 8. So essentially, if we put this over 1, multiply top and bottom by 8, right? So that gives me 16 pi over 8. That's equivalent to 2 pi. So then when we add this, we get 15 pi on the top, right, all over 8. And 15 divided by 8, that's less than 2, right? Because 16 over 8 would be 2 pi. So we're good with this one, right? So we just needed to add it one time, right? And then for part B, we have theta equals 19 pi over 4. So same idea, right? So we have, 19 divided by 4 is bigger than 2 pi, right? So it's actually bigger than, 4 pi, right? So what we want to do is subtract 2 pi until we get a value between 0 and 2 pi. Right, so we take 19 pi over 4, subtract off 2 pi, which would be 19 pi over 4 minus 8 pi over 4, right? Because 2 pi over 4, 2 pi over 1, right? If we multiply by 4 over 4, that gives me 8 pi over 4, right? That's where I get that value from. So then doing this, so 19 pi minus 8 pi is 11 pi, and this would be over 4. And this is still greater than 2 pi, right? Because, 2 pi we said is equal to 8 pi over 4. So 11 is bigger than 8, right? So we can take 11 pi over 4, subtract off another 2 pi, which would be 11 pi over 4 minus 8 pi over 4, which equals 3 pi over 4, right? And that's less than 1 pi, so it's definitely less than 2 pi, right? So that's within our interval, right? So those would be the values that we would want, right? And notice that there's only one solution for these, right? Finding a coterminal within this short interval, we're only able to find one answer, right? So if for part A, if I add another 2 pi to that, I'm going to be outside this interval, right? And then here for part B, if I subtracted 2 pi again, I would be outside the interval as well, right? I'd be less than 0. Right. So then objective 4, we're going to look at computing arc length of a sector of a circle, right? So if we think about what we already know, right? So if I have a central angle, right? So remember, a central angle is an angle inside a circle, right? So I could label this theta, and this distance here is r, my radius, and remember this part here is the arc length, which is s, right? So remember that we defined a radian to be, so if I wanted to find the degree of theta in radians, right? Remember what I would do is I would take s and divide it by r, right? So I'm trying to figure out how many radius distances can I fit inside the arc length, right? So since I already know this relationship between theta, s, and r, what I can do is multiply both sides by r, right? And I can do this because r is not going to be equal to 0, right? R can't be equal to 0 because if I had a radius of 0, then I wouldn't have an angle, so that wouldn't make sense, right? So I'm multiplying both sides by r. I know r is not 0, right? Because we can't, when you have an algebraic equation, we can't multiply both sides by 0. That doesn't really make sense, right? Like if I have, 2x equals 9, it wouldn't make sense for me to multiply both sides by 0, right? We get 0 equals 0. What does that mean, right? That's not helpful. So that's why I mentioned that. So what we end up getting is the r's cancel each other out on the right side. So we get r times theta equals s. So I could rewrite that, just flopping the sides, we get s equals r theta, right? So this is a relationship for arc length, right? And it's important to note here that theta is measured in radians. Right, that's assumed in this original, relationship, right? We use that to define finding an angle measure in radians. Right, so when we use this equation, if the angle is given in degrees, we need to convert it into radians, right? So, example 7. We're asked to find the length of the arc made by an angle of 220 degrees on a circle of radius 9 inches. Right? So if we want to, I don't know, I'm a visual person. If we want to kind of draw this out. You remember here is 0 degrees. Over here would be 180. This is 90 degrees. This is 270, right? Just as a reference. So 220 is going to be in between 180 and 270, right? So somewhere here is going to be 220 degrees, right? And that's our theta, right? And then we also know that this part here is our radius, which is equal to 9 inches. Right, that was provided to us. Right, so remember theta needs to be in radians. So theta is going to be equal to 220 degrees, and I want to convert this into radians. So remember, to do that, we need to get rid of the degrees, right? So I put 180 degrees on the bottom and put pi on the top, right? Because pi equals 180 degrees. That's my unit fraction. So now the degrees symbol will cancel out, right? So what we end up with is 220 pi divided by 180. And we can simplify this down to be 11 pi over 9, right? So then now to find the arc length, we can use our equation, S equals R times theta, So this would be equal to 9 inches, right? That's the radius, times, and then theta is 11 pi over 9, right? So the 9s are going to cancel out. So what we end up with is 11 pi inches, right? And this will be approximately equal to 34.6 inches, right? Because pi, and hopefully you know pi is irrational, right? It's never ending. There's no pattern, so we can't write pi as a fraction, right? That's what I mean by irrational. So that's why we give it a funky name, and a symbol. It's something we use a lot as well. So basically, how I got the 34.6, right? I just rounded to one decimal spot, right? So let me pull up my calculator. So we can just take 11 times pi in your calculator. So there's a pi key here, and then I can hit enter, and then we can just round, right? So I rounded to one decimal spot, right? All right, so now we're ready for example. Well, we did example 7. At the bottom of example 7, we start maybe to see some application. So we're just reminded that the Earth is approximately spherical. So it's kind of interesting that the Earth isn't spherical, but it's approximately, it's close enough, right? And the most common way to locate points on the surface is by using latitude and longitude, right? So we can say latitude and longitude. Right, so I have just a diagram here reminding you of longitude and what latitude is. So then example 6 has to do with longitude and latitude and arc length, right? So what we're told is that Lincoln, Nebraska is located at 40.8 degrees north, 96.7 degrees west, and Dallas, Texas is located at 32.8 degrees north, 96.7 degrees west, right? And those angle measurements is longitude and latitude, right? So what you'll notice is that their longitudes are the same, right? They're both equal to 96.7 degrees. So the cities are north to south of each other, right? So using the difference in latitudes, we want to approximate the distance between the cities, assuming that the radius of the Earth is 3,960 miles, right? So let me just make a note of that. The radius is equal to, what was that? Oh, 3,960. Oops, that looks bad. 3,960 miles. Right, if you want to draw a picture of this, right, I'm not a great artist, right, but essentially we have this sphere. Here's the center of the sphere, and over here and over here we have Dallas and Lincoln, Nebraska. Here's theta. Here's S, that's what we're trying to find, right? And this distance from these points is R, the radius, right? So since they have the same longitude, the difference in their latitudes are going to be equal to theta in degrees, right? So theta is equal to 40.8 degrees minus 32.8 degrees, which is, I'll call this, well, no, this would be fine. So theta equals 40.8 degrees minus 32.8 degrees, which equals 8 degrees, right? But we want theta to be in radians, right? So this would be equivalent to 8 degrees times pi over 180 degrees, right? So the degrees cancel. So what this simplifies to be is 2 pi over 45, right? So then now we know the relationship for arc length is you take the radius times theta, right? The angle measure in radians. So this would be equal to 3,960 miles times 2 pi over 45. And this comes out to be 176 pi miles, right? And then so using my calculator, this is approximately equal to 553 miles. Right, because we're asked to round to the nearest mile. Right? So if I go in into my calculator, right, and just, show you how I'm getting these calculations pretty easily with my calculator, right? So like to calculate S, I took 3,960 times 2 pi. Actually, I'm not going to put the pi symbol in. I'm just going to do 2 divided by 45, right? And what that does is that's where I get the 176 from, right? So I know that's 176 times pi, right? So in other words, I'm thinking about pi being a separate factor, right? So if it makes sense for me to write this out, so for here, I'm thinking of this as 3,960 times 2 over 45 times pi, right? Those are equivalent. So then I'm doing this part in my calculator to figure out that factor, the coefficient for pi, which is 176. And then, we can take the previous answer, multiply that times pi, and that's where we can round, right? So if we round to the nearest mile, we get the 553, right? So not too crazy, right? So then the next question I have is what does Google Maps estimate? Why are these different, right? So in other words, if we go in to here, let me just go to Google Maps. So we want to search the distance between, let's say we're traveling from Lincoln, Nebraska to Dallas, Texas, right? So if we go to Google Maps, notice it's estimating that it'll take 9 hours and 27 minutes to drive there, and it's roughly 638.9 miles, right? But the miles that we had gotten was approximately 553 miles. So I'm asking, why are these different, right? Well, they're different because the Google Maps distance, these are going on roads, right? So like if I open up the Google map here, you'll notice that the total miles are driving on these roads, right? The interstates and whatnot. But notice it's not a straight line, right? What we found was if we drew a straight line, what the distance would be, right? So basically thinking about it, like if I flew there, how far would I fly versus driving, right? So that's why they're a little different. And then the next part, so you can write that down if you wish. And the next part, I had just an interesting fact we could write down. So I have this written on the filled in notes. So I'm not going to write it on here for time's sake, so you could refer to that if you want to copy it down. But I'll just read it out loud. That the interesting fact is that the Earth rotates at a constant angular speed of 360 degrees in 24 hours, which is 15 degrees per hour, right? So each time zone is approximately 15 degrees of longitude in width and is 1 hour earlier than the zone immediately to the east, right? So like, for example, Chicago, right? Chicago's in the next time zone over, and they're 1 hour behind us, right? So it's kind of interesting. All right, so we have 2 objectives left to cover. So the next one is objective 5, which we want to compute linear and angular speed And I want to try to help demonstrate the distances between the two. Right. So let's say I have like a tire. Right. So here's my tire. I have a center of the tire, and let's say I draw this ray in here, and I'm going to call, let's say I'm going to call this point A on the tire, and this point B on the tire. Right? So then let's say the tire is going to move, after, I don't know, 15 seconds or something, right? We'll have some time that goes by, the tire will move, and so now the new position of A is up here. So we'll call this A prime, and the new spot of where B would be here, B prime, right? So in other words, we had a rotation, the tire rotated this in this direction, right? So this A point traveled along this path, and B traveled along this path, right, to get to A prime and B prime, right? So this is my tire, right? So let's say I call the distance that A traveled S1, and the distance that B traveled S2, right? So it's important to note that S2 is greater than S1, right? So if you've ever ran track, for example, you would know that's true, right? So like, I don't know if I can pull up like a high school picture of a high school track. Let me see if one will come up. So I was hoping for more of a bird's eye view. See what this. All right, so we can kind of see it with this. Let me just throw this image into OneNote so I can write on it. All right, so what I was trying to point out, if you've ran track before, let me see if I can find a good color that'll show up here. You'll notice that these spots here are staggered, right? The starting, let's say you're running like a 400-meter dash, right? So you'll notice these parts here are staggered. They're not all lined up, on the same row. But then, you do one whole lap, and then the finish would be here, right, roughly. So the whole idea of that is the outside lane, the person traveling along the outside lane would run further if we start and stop in a straight line, right? Because the inside track, the inside lane is the one full rotation is going to be smaller than like the outside lane, right? So that's kind of the idea going on here. So that's kind of a, an application that comes to mind from that, maybe thinking through your experiences. So that's why we know that S2 is going to be greater than S1, right? Because of that kind of phenomena, right? It's going to be going a greater distance, right? But the angle that was, the angle in between A and A prime and B prime would be the same, right? So angular speed is essentially, you know, how many radians did you go in, you know, 5 seconds or so forth, right? So in this case, the angular speed would be the same for both A and B. But we would have what we call different linear speeds. So the linear speed would be the distance the point traveled, right? So like S1 and S2, given a certain amount of time, right? So let me write a few things down here. So we're going to have the same angular speed, right? And the rationale is that they're going to move through the same angle for a given unit of time. Right? So you can think of, you know, like the angular speed maybe being in like radians per second. Right? The radian, you know, if this is theta, would be the same for points A and B. Right? Going from A to A prime and B to B prime. However, we're going to have what we call different linear speeds. Since S2 is greater than S1, right? We traveled further. So if you're traveling further in the same amount of time, you're going to be going faster, right? So, you know, if 1 hour I was able to run 10 miles versus someone who ran an hour who ran just a mile, that would mean that I would be going faster, right? So in other words, B travels further in the same amount of time. Right? All right. So then I have some other things I want to write down here for you. So I'm going to introduce a Greek symbol I don't know if you've used before. It kind of looks like a W almost. It's called omega. Right? So we're going to use this symbol. So let me introduce some equations here. So if a point on a circle of radius r moves through an angle of theta radians in time t, the angular and linear speeds of the point R. So the angular speed, we calculate, so we use omega to represent the angular speed. And what we would do is just take theta, their degree measure, and divide it by t, right? How many radians did you go in t seconds, or, you know, t time, right? So then linear speed, where we're concerned about how far did you go, right? So we'll use the variable v for linear speed. This would be equal to s, the distance, divided by t, right? Divided by time, right? Or what we could do is remember that s equals r times theta, right? So in other words, v would be equal to, so if I plug r theta in for s, we would have r theta divided by t, right? And then something kind of interesting is that theta divided by t is equal to the angular speed, right, omega. So what we could do is I could rewrite this as r times theta over t, right? That would be the same thing. And then theta divided by t is equal to omega, right? So this part is omega. So then this would be equal to r times omega, right? So in other words, or we could get that v equals r times omega, times the angular speed, right? So we have kind of three different equations that we can think about linear speed in terms of. All right, so we're ready for our last page for this video. So we have an example, something to introduce the area of a sector in the next objective, and then another example, and then we'll be finished, right, for this video. So example 9, we're told a bicycle wheel rotates at 2 revolutions per second. Find the angular speed, right? So if you're going around 2 revolutions per second, right, what that means is if this is my bicycle tire, here's the center of it. Here's kind of like, my point A, if you will. I have this ray here with point A. And if it's going around 2 times, right, so it's going around once and then again, right, that means that point A traveled 2 revolutions, which is equal to 4 pi radians, right? So remember, for angular speed, we calculate this with Greek letter omega, which is equal to theta divided by t. So theta here would be 4 pi, right, because we're going 2 full rotations. And the time here says per second, so this would be 1 second. So we went 4 pi radians in 1 second, which would just be 4 pi per second, right? And then part B, we're asked how fast does the bicycle travel in feet per second if the wheel is 2.2 feet in diameter. Right, so the diameter is equal to 2.2 feet. So what we're asked to find here is the linear speed, which is v equals r times omega. Right, I'm using that version of the calculation because we already found omega in part A. Right, so to figure out r, remember the diameter is equal to 2 times r. Right, so in other words, this implies that 2.2 feet equals 2 times r. So if I divide both sides by 2, we get r equals 1.1 feet. Right? So so what we have is that my angular speed, or excuse me, my linear speed is equal to 1.1 feet times 4 pi per 1 second, right? Which equals, so if we multiply straight across, what we end up getting is that this is approximately equal to, right? So we're asked to round to the nearest tenth, right? So if we throw that in your calculator, round nearest tenth, you should get 13.8 feet per second, right? So then I kind of have just like a question off to the side because, I mean, a lot of the times we don't think about feet per second and speed. The most common unit of measurement that we have experience with speed is typically going to be miles per hour, right? We ride in a car a lot of times, many hours of our lives, and that's what we kind of become accustomed to, right? So that's more familiar to us. So I'm just wondering, to put that in perspective, how fast is this? Right? So maybe put this into miles per hour to help with that, right? So in other words, if I convert 13.8 feet per 1 second. I want to convert this into miles per hour, right? I can use the idea of unit fractions, right? So I want to get rid of feet and make this miles, right? So there's 5,280 feet in 1 mile, right? So in this case, the feet are going to cancel, and so right now what I'm in miles per second, miles per second right now, right? And then so I want to leave the miles alone, but I want to get rid of the seconds. And I eventually want to get that into hours, but it might be easier to go to minutes first. So there's 60 seconds and 1 minute. So now the seconds will cancel, and right now the unit that we're in is in miles per minute. And then so now we want to make the jump to get miles per hour. So we want the minutes to go away. So there's 60 minutes and 1 hour. So since minutes are on the top and minutes are on the bottom, that goes away. So now we're finally in miles per hour, right? Those are the units that are left. So if I multiply straight across, what you should get from this is roughly, so approximately 9.4 miles per hour, right? So that's going pretty quick, right? Going about, roughly 10 miles an hour. That seems pretty quick to me on a bike, right? So it helps put it in more perspective. All right. So then the next objective that we want to look at is computing the area of a sector of a circle. So let's kind of draw a picture of what we're thinking about. So if we have a circle, and let's say this is like my initial side, and here's like my terminal side, and let's say this is theta degrees, right? And this, of course, would be r, my radius. What I'm trying to figure out is what's the area of this like slice of pizza, right, or slice of the circle, right? So essentially the way we can think about it is we have a portion of a whole circle, right? So the way I like to think about it is the area of a sector is going to be equal to the fractional amount of the full circle times the area of the full circle, right? So for example, if I have half of the area of a full circle, if I calculate the whole area multiplied by half, that'll give me the area of the sector, right? So the area, the area of a circle, I'll just do this, area sub circle, is equal to pi r squared, right? That's, a fact that we need to use. So, continuing on the area of a sector, so let me move this away. I put that over here. So back to the area of a sector, this is going to be equal to, so how do we figure out the fractional amount of a full circle? Well, what I can do is figure out the angle theta and divide it by 2 pi, right? So if I go pi around, that's half a circle, right? So that fraction is going to work out, right? If I take the radian degrees and divide it by 2 pi, that will provide me with the fractional amount of the full circle. And then I need to multiply this times the area of the full circle, which is pi r squared, right? Another thing that we could have put in here, if theta was in degrees, is theta divided by 360 degrees, right? But I chose to put pi here intentionally because pi is on the bottom here and pi is on the top here with the area of the circle. So the pi's are going to go away. So this is going to come out, to be pretty nice and neat. So the pi's go away, and what we end up with is 1/2 r squared theta, right? where of course theta is understood to be in between 0 and 2 pi, right? Not including 0. Right? We wouldn't be including 0 because it wouldn't make sense to find an area of a sector with an angle of 0 radians or degrees, right? So, so in other words, what we have is A equals 1/2 r squared theta, where A equals the area of sector of circle, r is equal to the radius, and theta equals the central angle in radians. Right? So then example 10, we have that a sprinkler rotates through an angle of 120 degrees and sprays water a distance of 30 feet. Find the amount of area watered, round to the nearest whole unit. Right? So essentially, you know, if you want to draw a picture of what's kind of going on, we have this sprinkler here. You know, it's going through an angle of 120 degrees, is rotating, and the water is going a distance of 30 feet, right? So that's the radius then of the circled path, right? So there's 30 feet. We have 120 degrees. So this is the area, area for the area watered, right, that we want to try to find. So there's a couple of ways you can go about this, right? The very first thing we can do is try to convert 120 degrees into radians. So theta is equal to 120 degrees, which is equal to 120 degrees times pi over 180 degrees, which is equal to 2 pi over 3. Right, just simplifying that down. So then the area of the sector, you know, just using that equation, would be 1/2 r squared theta. Right, so filling in what we know, we'd have 1/2 times, so r squared is, r is 30, so this would be 30 feet squared times theta, which is 2 pi over 3. And then you can simplify this down. This will end up becoming 300 pi feet squared, which is approximately equal to 942.478 feet, square feet. And let's see, we're asked it around to the nearest whole unit, so we would get 942 square feet. Right, so that's one way to go about it, right? But something that, you know, I've told my classes before is a lot of times, like, you know, this is a nice, neat equation. I get, you know, where it comes from, but it's not, you know, you don't have to use that equation. In fact, that equation is not something I memorize, right? I think trying to think about something more conceptually and figure it out, you know, without using that equation for this type of problem, goes a long way, right? It's hard to memorize everything. You can't. So if we can just kind of memorize what's or understand what's going on a more logical level, we can come up with this area another way, right? So for me, you know, this is, you know, second way method, and this would be how I would do this problem, is I would just say the area is equal to, so all right, so we're going 120 degrees out of a full rotation, which is 360 degrees, right? That's my fraction of the circle. So this is my fraction of the circle. And then here, I just want to multiply by the area of the circle, right? Which is pi r squared. So this would be pi times 30 feet squared, right? Pi r squared. So then if I multiply these together, I'll come up with the same amount, right? So it'll work out to be the same, right? And we can verify that using a calculator. Right. So if I take 120 divided by 360, I multiply that times 30 squared, and then multiply that times pi. You can see we still get the 942 square feet, right? All right, so that's all I have for this video. I'll be making another short video going through some more examples from 5.1. Let me know if you have any questions. Thanks.